So we are now ready to construct an action for the vector field from which to derive equations for motion which we expect will be the two missing Maxwell equations. This action has to satisfy several conditions. The first of them, the simplest, will be that it has to be gauge invariant. This means that we cannot use a mu as such. We have to use f mu nu, which is gauge invariant. Okay, f mu nu depends on A, contains derivatives, first derivatives of A. Remember that we can write it in this way. So if we construct Lagrangians which are quadratic in f, then we will have something which is has two derivatives of A, which is the right combination, the simplest. Another condition is that it has to be Poincare invariant. And by now we know that it is enough to construct combinations in which all the indices are contracted, and so there are no free indices anymore. So in 4 dimensions, and this is important, okay, there are the following invariants that can be constructed, okay, in the equal for, say here, that can be constructed from f mu nu. The first invariant is what usually we write f squared, and f squared is f mu nu, and if I write this showing the metric, it would be eta nu alpha, eta nu beta, f mu nu, f alpha beta. Well, in order to get some intuition, and also for other reasons, it is important to see what this f mu nu or f squared is in terms of the standard electric and magnetic fields. So let me just do it. So we have to split these indices mu and nu into zeros and i's. So let's first split mu. So first it can be 0. Oops, this is, sorry, nu, I'm not touching nu. And then you sum over I nu f I nu. Next, I split the index nu, but nu cannot be 0 because of the antisymmetry of f mu nu, so this can only be a special index I. Plus, then nu can be 0 here, and there can be also some other special index j. Ij, Fij. Now f0i, if I interchange these two indices, I know that this is minus ei, this is ei, so this is minus ei, ei. And here in the second term I will interchange these two, and this would be ei and this minus ei, so in total I get minus 2 ei. And here I have to assign that is irrelevant because this appears square. I get I know that this is epsilon ijk bk and epsilon ijl bl. So these are three-dimensional objects. I don't care if I write the indices up or down. I just need to consider the contraction of these two epsilon symbols, which I know gives 2 delta KL. Okay, so this is minus 2 ei minus bi, or if you want, minus 2 e squared minus b squared. The value of this combination of the electric and magnetic fields will always be the same in any inertial reference frame. This is important for many reasons, but just to give you an example of how you can use this, suppose that f squared is positive. Okay, looking at this expression, you know that there must be a magnetic field which is different from zero. Okay, there might be some electric field whose square is smaller than b squared, but whether there is E or not, we just don't know from this invariant. All we know is that at least there is a magnetic field, and this is different from zero. Now, this is true in any reference frame, inertial reference frame. So if I make a Lorentz transformation, suppose that because Lorentz transformations mixed E and B, you can generate, suppose that there is no electric field at the beginning, you can generate E, but you can never make B disappear because this sign will always be positive. So the magnetic field is not something that can be generated by Lorentz transformations, and it has a real existence. If you have it, you cannot make it disappear. Okay, you can make appear a magnetic field appear. Okay, if you start with f squared smaller than 0, you know that the electric field is different from 0. You don't know if B is 0 or not. Suppose that it is. Okay, I can make it appear, and it will not violate this situation because E squared will still be larger than B squared. But I cannot make it disappear. So it is not, although their value is not completely fixed, it is not something whose existence is irrelevant. So it's not that there is electric field and then the magnetic field is something derived from it, and due to the fact that things move, as some YouTubers claim. In 4 dimensions, okay, f squared exists in any dimensions, but in 4 dimensions I can construct a second invariant that has this expression, and because in 4 dimensions I have a completely antisymmetric symbol which has precisely 4 indices. Okay, in 5 dimensions the epsilon will have 5 indices, and then I cannot contract it with the 4 indices of 2f's. So this is the second invariant, and again we can try to see if what is the expression of this guy in terms of the electric and magnetic fields. This is not a difficult calculation, but it requires some gymnastics. Okay, first I want to see how many times f0 can appear here. It can appear 4 times in mu, in either of these 4 positions. So I will get a factor of 4 times epsilon 0 nu rho sigma f0 nu f rho sigma. Okay, you probably have to expand this and treat it carefully and interchange indices and so on to realize that indeed these two things are equal. At the moment I have an index 0 here, nu, rho and sigma can only be spatial indices, so this is actually only for epsilon 0 I j k f0 I f j k. Okay, so this part of these 4-dimensional antisymmetric indices, okay, this when one of the indices has been decided to be 0, is just like epsilon ijk. It has the same property. So when ijk is 1, 2, 3, this takes the value 1, and other permutations give you -1 or +1. So I replace this by epsilon ijk. f0 I f jk, then I know that this is ei, so I have 4 times I, and I know that epsilon I j k is minus 2 times bi. As I said, the index up or down doesn't really matter once this is expressed as a three-dimensional object. So this is minus 8 ei, sorry, times b. Okay, this is another invariant, and this tells you that whatever in any whatever the inertial reference frame, if this is 0 at the beginning because one of the two fields is 0, this will still be 0 after a Lorentz transformation, because I will generate, suppose that I have b different from 0 but e equal to 0, I will generate a vector e, maybe, but this vector that I will generate will be orthonormal to the b, orthogonal to the b that I had. Okay. Now the problem is these two invariants have the right number of derivatives, so I could try to construct actions with them. But this second invariant has a big problem. Okay. Let me show you what is the problem. So we can write it like this. Remember that f mu nu is 2 times partial mu a nu antisymmetrizes. This is contracted with it, which is antisymmetric. I don't need to antisymmetrize. And now let me integrate this by parts. So I have partial mu of all these things, mu nu rho sigma a nu f rho sigma minus 2 epsilon minus partial mu minus 2 epsilon mu nu rho sigma partial mu f rho sigma, and then outside of the derivative a nu. I am using the fact that I can put this epsilon inside or outside of the partial derivative. Now this, the three in this expression, these three indices mu, rho, and nu are contracted with three indices in epsilon, which is completely antisymmetric. So these three indices are completely antisymmetrized, even if I don't write it explicitly. But the Bianchi identity tells me that this is automatically 0. What this means is that, okay, if I call this w mu, this is clearly a total derivative. If I write a Lagrangian with only this term, this Lagrangian will be equivalent to the zero Lagrangian, because it will give the same equations of motion as the zero Lagrangian, because the difference between 0 and this is a total derivative. In other words, the equations of motion will be trivial, so it doesn't give you anything. You cannot use this term in 4 dimensions to construct a Lagrangian, a viable Lagrangian for the electromagnetic field. Observe that if I multiply this term by some field, okay, then this field cannot be put inside of the total derivative, and this will not be a total derivative anymore. So if I had a field which has to be a scalar, okay, in order for this to be Poincaré invariant, okay, if we were much more precise when we took into account improper Lorentz transformations, we would conclude that this phi has to be a pseudo-scalar, but let's not get into that. Okay, in that case, this could give you non-trivial equations of motion, and this field is would be what is called an axion. This is just a curiosity for you to know. Okay, the conclusion is that basically the only possibility is the term f squared, and okay, we just need in order to write this action, we need the for x, and we have f squared but we need to know what is the right normalization of this, assuming always that we take this standard canonical convention that we want something that has 1/2 of derivatives of time of the quantities squared. Okay, so let's see what is the number that we have to put there to have that canonical normalization. Okay, this is just a conventional thing. Okay, and okay, I will profit from the equation that this decomposition that we found before. So this is just f0i plus fij once I put all the indices down, and f0i by definition is partial 0ai minus partial I a0. Okay, if I manage to remove these terms, then I get that this first term here would be quadratic inverse derivatives of ai. How can I do that? Okay, I can use a gauge transformation to remove a0, to set a0 equal to 0. How do I do that? Okay, I want a prime 0 to be 0. Okay, this is what I want, but I know that a prime 0 will be a0 plus the time derivative of some function. So this function satisfies this equation, minus a0, and this equation can be solved immediately. I just need to integrate. So chi will be minus the integral to 0 of, now I use some other variable, of a0, and so I have replaced x0 by y0 to integrate, and the result of the integral, I integrate between something and x0, and this gives me chi. So I can do this, and in this gauge, okay, in the gauge a0 equal to 0, I get this is just partial 0 ai. And now I come back here, and this is minus 2 partial 0 ai partial 0 ai plus something that contains only ai's, but it cannot be interpreted as a kinetic term. So if I want this to be 1/2, what I need is a normalization factor of minus 1/4, and this will be the Maxwell action in c equal 1 units. Okay, now that we have the action, we can find the equations of motion, and then if we rewrite these equations of motion in terms of the electric and magnetic field, we can compare with the two missing Maxwell equations. The simplest way to do this, we can always use the Euler-Lagrange equations, but the simplest way to do this is to vary the action and find the term which is proportional to delta A mu, and identify that as the equations of motion. Okay, so we vary the action. This variation is as the variation of the fields, and we have we have d for x. X is not modified. Then I have minus 1/4. Then I vary f mu, so I get f mu nu plus f mu nu delta f mu nu. I'm doing this well, in full detail. Of course, in this variation, I can raise or lower these indices with the metric eta mu nu, because the metric is not varied at all. This means that if I raise these two indices and I lower these two indices, I get exactly the same, or vice versa. Then I get a factor of 2, the integral d for x, the factor minus 1/2, and then I use delta f mu nu. Okay, now I use the definition of f mu nu, and this is minus 1/2 the variation of partial mu a nu with a factor of 2. that cancels this 1/2 and then f mu nu. Since this is contracted with f mu nu, which is antisymmetric in these two indices, then I can remove these antisymmetrizers. So this is exactly the same. This variation commutes with the partial derivative because it doesn't act on coordinates, so I have partial mu of delta A nu. So let's write this result now. We have minus partial mu delta A nu f mu nu. And in order to find something proportional to delta, I have to integrate by parts. So this is minus partial mu of delta A nu f mu nu plus delta A nu partial mu f mu nu. Okay, we know that this term can be eliminated by assuming that on the boundary delta A nu vanishes. I just use the Gauss theorem. So this term cancels, and we can identify this term, since here we have delta A nu, as delta S delta A nu. And the conclusion is that delta S delta A nu is f mu partial mu f mu nu, and the equations are that this is equal to 0. In this context, in which we are using A mu as a fundamental variable, this is known as Maxwell equations. And we expect that they give the two standard Maxwell equations in terms of the electric and magnetic field, because the other two are equivalent to the Bianchi identity. So let's see if this is true. So first, I separate this equation into equations with the free index nu equal to 0 and I. So when nu is 0, I have f mu 0, and this is okay. Now I split the index mu into 0 and I, but it cannot be 0 because I already have 0 here. So the only thing that survives is partial I fi 0. I know that this is the electric field, so I can write it like this in components, and this is what it's usually written in this way. So the divergence of E is 0, and this is one of the Maxwell equations we were looking for. Now if nu is I, then I have mu can be 0, but it can also be j, f j I. This is minus the electric field minus partial 0 E I, and this is minus epsilon j I k, which I already take out of the partial derivative, partial j b k. Then we interchange these two indices and we get a minus, and as a result we get partial 0 I plus epsilon I j k partial j b k. As usual, this is the ith component of the vector product of this operator times magnetic field. So if I write everything in vector notation, what I get is, up to the overall sign that I change, this equation, which is the last missing Maxwell equation. Okay, so that these two equations and the other two are related by E going to B and B going to minus E, which is the electromagnetic duality transformations that I mentioned before. If there were sources, charges, currents, then the right hand side of these two equations would not be zero, and then this interchange would not work. Okay, so they only work when there are no sources, which is what we usually call the vacuum in this context. So now that we know that these Maxwell equations are the two missing Maxwell equations in terms of E and B, let's see what they are like, what they look like in terms of the electromagnetic potential. So I have to write F mu nu now as partial mu A nu minus partial mu A mu. Okay, this is because clearly the metric can get inside of the partial derivative and raise the index inside of the partial derivative. So this gives us what d mu, which is what we have called box, the Dallon version, sorry, minus d mu A mu. Okay, this is not a familiar equation, but we can interchange these two partial derivatives, and we get this. Okay, this inside of this derivative. And now I claim that there is another gauge choice that one can make just to simplify these equations and to bring them to the more conventional form, which is this gauge, which is called the Lorentz or covariant gauge. So what I'm claiming is that after a gauge transformation, I can get an A prime, which is 0, and I know that this is the divergence of A mu plus, now written in this way, this is like this, so it is box chi. So if I want this to be 0, I just have to solve this equation, which is not simple, but can always be done. This is the relevant thing. This means that I can always choose this gauge. So this is the Lorentz or covariant gauge. And in this gauge, what I get is that each separate component of the vector field satisfies the Klein-Gordon equation, the massless Klein-Gordon equation, which is the wave equation, box A equal to 0, A0, A1, A2, and A3, which is the equation that the massless scalar field also satisfies. Now, as we have done already several times, after we find the equations of motion, we want to find the conserved quantities and analyze, which means analyzing the symmetries of this action. Before we analyze the Poincare symmetries, which will lead us to the energy momentum tensor, just as in the case of the scalar field, we are going to see what happens with the gauge symmetry of this action. We know that this action is invariant under the transformations chi, which are of this form, and that we can consider infinitesimal if this chi is very small. So we know that this is 0. And now if we vary the action, okay, as before, we get a factor of 2 F mu nu and the variation of just one of these F mu's. Then I know that this is 2 times this anti-symmetrized, so this variation commutes with the partial derivative, so I get it inside. I get another factor of 2, and this is just minus F mu nu partial mu delta chi A nu. Okay, then I integrate by parts, and I get this total derivative f mu nu delta chi a nu plus the equation of motion delta chi a nu, which I now write explicitly. Okay, sorry. Now I want to integrate this by parts again. For x I can also write this, so I have another partial derivative of partial mu f mu nu chi minus partial mu f mu nu chi. If I interchange mu and nu, I think this is mu and nu here, then up to a sign I get minus partial mu, and then I have f mu nu partial nu chi plus partial nu f mu, sorry, I should write mu nu, yeah, indeed, chi minus partial mu f mu nu chi. Okay, this is another total derivative, so this is minus partial nu f mu nu chi. Okay, I know that this is 0 because of the antisymmetry of f mu nu and the symmetry of two derivatives. So let me ignore this piece, and I know that this is also going to be 0, but suppose that it wasn't. Okay, the point is that gauge symmetry, the fact that this is 0, okay, forces you to have this equal to 0. So this is a, if you want a trivial identity, the fact that you can write it like this, that the equation of motion of a nu satisfies this condition of shell is trivial. I mean, it is obviously satisfied always of shell, but you can say that it is thanks to this identity that you have gauge symmetry. These two things are related as usual, and this, now if you read it in this way, it tells you that not all the Maxwell equations that you find, the 4 equations that you find, are really independent, which agrees with the fact that we expect less degrees of freedom, less independent equations. So this would only describe 2 degrees of freedom instead of 4. The counting of degrees of freedom and counting of constraints is complicated, but indeed you can show that this symmetry, okay, the gauge symmetry that we have, a mu equal to a mu prime equal to a mu plus d mu chi, can be used to remove 2 unwanted degrees of freedom. Okay, now the important thing about this symmetry and this identity is that it constrains very much what we can couple to the vector field. So suppose that we had, as we will write later, some current, okay, which is a source of the electromagnetic field. We know that this would be the Maxwell equations. We will find this later on. But if we take the divergence of these two sides, this is 0, okay? But and this implies that for consistency this has to be 0. But we know that this is a conservation law. Now it is important to realize that this J is not the nether current. Okay, it is a conserved current from some other field, which for example describes electrons or some other kind of charged particles which are coupled to the electromagnetic field. However, that current is conserved because otherwise it cannot be coupled to the electromagnetic field consistently. Okay, we will see this in more detail. Let us now consider the consequences of the invariance under Poincaré transformations. We will just focus on translations, space-time translations, and we know that one should get a set of currents labeled by the index of the different parameters of the space-time translations, and that this set of currents corresponds to the energy momentum tensor. Now, the same calculation we did for the scalar field gives the conservation of this object in general. Okay, this is what we got there. But in this case, so this is, you can see this as a generic calculation in which instead of phi you have any series of fields. So what happens if one has the vector field a nu, then you have a sum over the index a nu. Now for translations, what you have is that this is alpha mu, which remember is alpha rho, say delta mu rho, and for translations delta a nu is just minus alpha rho partial rho a nu, just the transport term. Okay, so you come here and you find, taking alpha rho as a common factor, the conservation of L delta mu rho minus partial L partial mu a nu, and then partial rho a nu equal to 0. So this is T mu rho for the electromagnetic field. Let me write it here. Okay, so this T mu nu, now I use mu and nu indices, is given by L delta mu nu minus partial L with respect to partial mu a nu. Sorry, now I need to replace this by something else, and partial nu a rho. Okay, let's do the calculation. L is minus 1 over 4 f squared, then we have delta mu nu minus, and the derivative of L with respect to partial mu a rho is minus just f mu rho partial mu a rho. Okay, I did this calculation, sorry, with plus, I think. Okay, so how did I do this calculation? Remember that we can write L is minus 1/4 of f squared, so this is minus 1/2 of partial mu a nu f mu nu. This is one way of writing it. okay, where I use that f mu nu is 2 times this antisymmetrized, this is contracted with these indices, so the antisymmetrization here is implicit. Now, in taking the derivative, I get a factor of 2 because, okay, this really has d mu a nu here and d mu a nu here. So you are going to get another factor of 2, so it is minus. This is the implication that this is just minus f mu nu. Okay, so this is the energy momentum tensor, and okay, let me remove this from here. The first thing we can do is to check that it is conserved indeed, using the equations of motion, which are the Maxwell equations that we just derived. So we take this derivative, this is minus 1/4, and d mu and is contracted with this delta mu nu, so this is just partial nu f squared, plus then I get two terms, partial nu a rho plus f mu rho partial nu a rho. Okay, so first we are going to interchange these two partial derivatives, and we are also going to use the equations of motion, because we know that the conservation of nether currents is always an on-shell business. The equations, these are the Maxwell equations. This is equal to 0, so we just forget about this term, and then we get partial nu f squared plus f mu rho partial mu a rho. Now this is antisymmetric in mu nu, so this is automatically antisymmetrized in mu rho, and then this is a half of f mu rho 1/4 partial nu f squared plus a half of f mu rho partial nu f mu rho. Now this is just a half of partial nu f squared. Okay, because you would have you can raise and lower the indices of these f mu nu's inside of the partial derivative, and this means that this term and this term cancel automatically without using any equations of motion, so this is equal to 0. Okay, it is on shell because we have used the Maxwell equations here. So you could say that this energy momentum tensor is perfectly fine, but observe two things. This energy momentum tensor, well, one of the properties that we would like to have is that it is symmetric if I raise or lower the indices. Why? Well, for the moment, because clearly, I mean, this a set of currents J mu nu doesn't have to be symmetric, but we would like it to be symmetric for reasons that will become apparent later. Okay, this is not symmetric, so this property, which will become important later, is not satisfied. A more immediate problem that we see is that this t mu nu does not depend only on f. It contains this partial derivative of nu with respect to nu of a rho, but this is not f nu rho. There is a term missing here for this to be f nu rho. This means that this t mu nu that we have computed is not gauge invariant. So if I take a gauge transformation of t mu nu, this is not 0, and this is a more important problem. Okay, if you want, this is a technical problem. The reason why we have obtained this result, even though the action is gauge invariant, has to do with the transformation law that we have used for the vectors under space-time translations. The reason I doubt whether to say it or not, because probably you will get more confused, is that a field that has a gauge freedom is not really a tensor in this standard sense. It's a field which is more complicated, and its transformation law under space-time transformations of any kind always involves some kind of gauge transformation. Once you include this gauge transformation, one finds that the energy momentum tensor that results from this modified transformation is gauge invariant. Okay, we will not get into that, and we will do something simpler, if you want, which is the following. When we have a conserved current, okay, so this current is such that it satisfies this, you can always modify J mu by adding things like a term, let's say A of this form, partial mu A mu nu. So you have something which is antisymmetric. Okay, you take a partial derivative with respect to one of these two indices, and this J mu prime that you get is automatically conserved as well, because partial mu J prime mu is partial mu J mu, which is 0 on shell, plus partial mu A mu nu antisymmetric, but this is antisymmetric, this is symmetric in mu nu, so this is 0, and again this is 0 on shell. Furthermore, we could add okay, there is a second modification that one can make to a conserved current, which could be to add to J mu any term. Okay, you can multiply this, for instance, for some function, whatever, proportional to the equations of motion. I mean, clearly, if you do this, when you take the derivative, it doesn't really matter that the divergence of this. What you get from this will always be proportional to the equations of motion and will vanish on shell. So this is another modification that you can do. In this case, the modification that we want to do, we want to add to T mu nu. So let me write this T prime mu nu will be T mu nu minus this term. I mean, this is the term that we clearly need to write this, to convert this into F nu rho and to have gauge invariance. Okay, so this is the motivation of adding this, but observe that this term can be written in this way by integrating by parts. This is partial rho of F mu rho A nu, and indeed this is a term which is antisymmetric in mu rho. So when I take the divergence, so a partial derivative with respect to mu of this term, I will have something symmetric in mu rho and something antisymmetric. So this vanishes, plus partial rho F mu rho A nu. Okay, and this is 0 because this is on shell, because these are the Maxwell equations. The order mu rho and rho mu, they are just different in a sign. So adding these two terms, this term is basically like this term. Okay, but here we have a collection of currents, and these functions have an index nu, and this is the A nu that I'm multiplying the Maxwell equations by, and this term corresponds to this kind of term. Because if I get another current which is also conserved on shell, that I call T prime mu nu, and this T t prime mu nu, when I compute it, is just okay, I prefer to write it in this way, is f mu rho minus 1/4 delta mu rho f square. It's gauge invariant, but also automatically gauge invariant because it is written all in terms of f, but also this t prime mu nu is equal to t prime nu mu, so it is symmetric. Both terms have been, both problems have been fixed at the same time, which is very nice. This is called the Belinfante energy momentum tensors. So why is this interesting? Because this is really the energy momentum tensor to which gravity will couple, and that's important enough. Finally, we would like to see what this energy momentum tensor looks like when we write it in terms of electric and magnetic fields. This is very simple. First we compute f squared, but this is something that we did before. This is minus 2 e squared minus b squared. Then we have to compute this for each component. So let's see, if we compute t 0, 0. Okay, so I lower the indices mu and nu. This is f0 rho, f0 rho minus 1/4, then eta 0, 0, which is plus 1, and f squared, which is minus 2 e squared minus b squared. Now, because this is 0, rho can only be I. Then if I lower the index, I get a minus sign, so this is minus ei, and this is minus e squared, and here I have plus 1/2 of e squared minus b squared, and then I get minus e squared plus b squared. Okay, and this is going to be the energy density. So this is equal to minus, okay, the energy density of the electromagnetic field. Without conventions, T0, 0, as we said, gives you minus the energy density. Then we can compute the components Ti0. So this is Fi rho, F0 rho, minus, and then eta 0i is 0, so we don't need to compute anything else. And because this is 0, rho has to be a space-like index, so this would be Fij minus Fij, because I lower this j, and I get a minus sign, F0j. This is Ej, and this is minus, so minus and minus, plus epsilon ijk bk, and then aej. So this is nothing but E vector product b and the ith component of this. This is, remember, the Poynting vector. And this is energy flux, or momentum density. Finally, we have to compute Tij. Ti0 and T0i are the same thing. So Tij, the calculation is a bit longer. So we have Fi rho f j rho minus 1/4 eta ij, which is minus delta ij, and f squared, which is minus 2 e squared minus b squared. Okay, this now rho can be 0. If it is 0, we get fi 0, fj 0, and if it is k, then I lower this index and then I get minus fik fjk, and here I have 1, 2, 3 minus signs, so it is minus a half delta ij e squared minus b squared. This is ej minus epsilon ikl epsilon jkm bl bm minus 1/2 delta ij e squared minus b squared. And now I move this case to the first position. I get 2 minus signs, which in the end give me a plus, and this is nothing but ej minus 2 times delta il comma jm bl bm minus 1/2 delta ij e squared minus b squared. Okay, now let's do this last calculation. This is ej minus this is delta ij delta lm. This is the first term, so delta ij is here, and delta lm gives me b squared plus delta im and delta lj, so this gives me bi bj. Well, I wrote the indices down here, but this is the same as up, as I said. E squared minus b squared, so this combines with this term, and we get ei ej plus bi bj minus half delta ij e squared plus b squared. Okay, and this the meaning of this term is that it is the flux of momentum. And here I refer always to three-dimensional momentum.